So actually, this is the last lecture. There is not really something prepared. Just going to summarize the ideas, and then you will be free to ask the last questions, either for the exam or more generically about modified gravity. So first of all, about a possible confusion. If you go on internet and you write modified gravity, you might find two types of modification of gravity. There is one, very often when we say modified gravity, people think to something which is related to dark matter. Dark matter is something I didn't talk at all about it, so let me just summarize it very briefly. If you look to a galaxy, so let us suppose that this is a galaxy, and you have stars in all that galaxy. It's like a pancake, it's something flat. What we expect usually, if you look to the solar system, for example, you have the sun, and then you have a first planet, which is Mercury, which has some velocity. And if you go at larger distance, usually what you have is the velocity will be smaller. More you are far and less the velocity is. What's happening is that when you look here, the stars which are very close to the center, or the stars which are here, if you look to the velocity, how it goes as a function of r, you get something which is it's increasing, and then you get something flat like this. So actually, all these stars which are at some distance from here to here, they have same velocity. The problem is these stars here, which are far, they have very large velocity. If they have very large velocity, they should just shoot out actually and leave the galaxy, because you have a velocity of the star, but at the same time you have gravitational field to the center. But the gravitational field is too weak because they are very, very far from the center. And they have very large velocity. If you spin something with very large velocity, the particle just goes away. And the problem is that they don't go away, actually. They stay in the galaxy. They maintain their motion in the galaxy. So how is it possible that you have a star, which has a so large velocity, but at the same time it keeps going here? So the idea is to say, what we observe in terms of matter in this galaxy, it's not everything. There is much more than that. There is everywhere here, we have some additional matter, which we will call dark matter. So if you include all this matter around, finally you can find a way that this velocity can be large, but stays inside this galaxy. If you have only the matter here, it doesn't work. That is for sure. So then people cooked some kind of models, which are, for example, a model which is called MOND. And very often, this is what people call modified gravity. So if you go on internet, on Google, and you search modified gravity, you will get principally theories like that, which is just a modification of Newton. Newton says that the summation of forces is equal to m times the acceleration. So they just modify this acceleration here by something. It's just a Newtonian theory. It's not at all a relativistic theory. So this is the idea of MOND. So careful when you search for modified gravity on internet. If you want to have more information, very often you will get this type of theories. What I talked about, very often they call it either modified gravity or beyond general relativity. So if you want to have more information, maybe you should check also beyond general relativity. So what is what we have seen? That we can have various motivations. one motivation can be some problems which do exist in cosmology, for example, what is called the dark energy problem, why the universe is accelerating. Is it a problem or not? It's debatable. Some people they say there is no problem. Some people they say there is a problem. So it's not completely actually clear. So, but if people consider there is a problem, then maybe we should go beyond general relativity. The other motivation can be inflation, also another acceleration of the universe, but in the very, very early universe. So we had two acceleration. When the universe starts, it accelerates, then it slows down, then it again accelerates. There are two accelerations, inflation and dark energy. So to explain that, very often we go beyond general relativity. That is just a direct kind of motivation. You observe something, you don't understand it, you go to some new theory. Other motivations, which are in some sense more fundamental, is to consider that GI is not the last word that we have about gravity, that it's not the most fundamental theory, that we know that it's not a quantum theory of gravity. So if we include quantum effects in that theory, we should have some sort of corrections to it. These corrections, for sure, they should be very important at high energies. If they are going to be important at low energy, it's not sure. So then you have two modified gravity theories. You have UV modified gravity, and you have infrared modified gravity. So this is a modification of gravity at high energy. The other one is a modification of gravity at low energy. So we talked principally during these lectures about this part, infrared modified gravity. That is the most complicated one in the sense of motivation. To say why should we modify gravity at low energy? Clearly at low energy, GR works well. We saw all the tests and it works perfectly well. You do experiments in a lab, you do experiments in a solar system, you do experiments around a black hole, a pulsar, a neutron star, at the scale of galaxies, cosmology, etc., etc. And it works perfectly well, actually. So then it's a bit more difficult to motivate it. I try to give some motivations like extra dimensions. Extra dimension can actually produce a modification of gravity at low energy. Some theories, at least, not all theories with extra dimensions. So that is some sort of motivation. You can read a bit more about what is called brain models. We talked about it a bit. It's an interesting field. UV modification of gravity, this is highly, it's well defined. It's motivated in the sense that we know that at high energies, GR cannot be the theory of gravity because it's classical. We need a quantum theory. So to say UV modified gravity, it's obvious. There is no point even to try to motivate it because, of course, at high energies, GR cannot be the theory, so you will need something else. So we have two approaches to that. So let me comment a bit more about infrared modified gravity. We saw that one way to do with that is to modify the action of general relativity, and very often it's equivalent to other scalar field. In FOFR, you can make a transformation, it's a scalar field. You can add a scalar field by yourself. You can take a brain model in 5 dimensions, reduce it, you get a scalar field, which is just the position of the brain. You can take a space-time, you compactify it, the radius will be the scalar field actually. So you can different ways, and very often it goes back to a scalar field. So then you want to study the phenomenology of that scalar field. Now, what the observations are telling us about it? Do we observe it or not? So I will look at it at different scales. First of all, constraints from cosmology. What cosmology is telling us about that scalar field? We have used the theory of perturbations, and that is a very important tool. You cannot just study the background. You cannot just study that the universe is expanding or not. That is easy in some sense. You have to go to the perturbations. And the perturbations, we saw that, for example, the density of matter gets some perturbation, delta rho, which depends on everything, T, X, Y, Z. What does it mean? Is that our universe is completely homogeneous and isotropic. We have the same density of matter everywhere. It just changes with time. But there are some places where there is a bit more density. So here there is a bit more density. And just because of gravity, this will attract more matter. So it will start growing, becoming larger and larger. And it's what we see today as galaxies, as structures. So it's very important to study this delta rho, or very often we define a delta m, which is just the normalized thing. You divide delta rho by rho. When you write your equation of motion for delta, you can find an equation which has this structure. So you have an equation which has this form, which tells you how this small perturbation is growing or decreasing with time, actually. And this is going to be your equation, and it comes directly from the equation of motion. In modified gravity, the gravitation constant here is not the gravitation constant, but some effective constant like this. That effective gravitation constant is very often time and space dependent. Now, the point is that you observe the universe, you observe the galaxies, how they form, so you can put constraints on that. And what do we have so far is that this is constant. It's just G. So far with the precision we have. So what does it mean also is that this does not depend on space. So most of the theories which do have a G effective which depends on space, that you have a gravitation constant which is not the same at small scales and at large scales, for example, they will have some troubles. And for example, F of R gravity. So we talked about F of R gravity. F of R gravity has a G effective, and we don't observe at all that, we observe only G. So F of R gravity is in trouble. So if you want to work with F of R gravity, you have to be very careful. You have to study all the equations and see, compared to the observations, fine-tune your parameters, etc., to be sure that the theory is working. So F of R gravity is, in some sense, in trouble already at this level, actually. Okay? So if you want to go in some field, in some direction, maybe this is not advised to go in that direction. There are other constraints. We saw that also, so for the most advanced ones which already started a PhD in that when we were doing perturbations, you had two potentials, two gravitational potential, psi and phi and psi. And in the theories of gravity, in GR, these two quantities are equal. And in modified gravity, they are not equal. And this we can constrain it. So far, the constraints are saying they are equal with the precision we have. So again, GR is perfect and it works perfectly well. What is going to give the last answer to that is an experiment which is going to start in around 2021. It's a telescope, a European telescope, which is going to start 2020 or 21, which is going to start actually collecting a lot of data. And one of them is to see if these two quantities are equal and to measure also the G effective. That is going to be more or less the last picture on that. We will know after that if it works or not. They will certainly take 1 year to collect data and then some time to process all that. So maybe around 22, they might publish the results. So maybe for the people who just start now, when they will be during their PhD, the results from that will come. So then we will know if these theories are interesting or not. if we go at smaller scales, let me give a few things that we didn't talk about, actually. What are the effects of these theories for principally the chameleon mechanism? Imagine we have talked about something which is called a screening mechanism. If you are in an environment which is very dense, you have a lot of matter, that scalar field couples to matter, and it becomes extremely heavy, and finally you don't feel it. If you are in some environment where there is no much of matter, it decouples completely, and it starts having some effect. This is the chameleon mechanism, and this is why it is called chameleon, because it has a mass which depends on the environment. Now let's look to the situation of two galaxies. You have a small galaxy and you have a big galaxy. What's happening is that the scalar field is everywhere. Let's suppose that the scalar field exists, and it is everywhere. Here, there is very little of matter. So the scalar field couples just a little bit, so actually it's unscreened. In the sense that you will feel the scalar field here. Here you have a lot of matter, so the scalar field just kind of disappears. It will be screened completely. So depending where you are, if you are in a small galaxy or in a large galaxy, you will see effects which are different because that scalar field couples to matter, to the environment which is there. If there is a small galaxy or a big galaxy, you will see different things. So a small galaxy follows just the Newton force. So there is from Newton, the large galaxy is following just the Newton force because there is no scalar field. But here, there is a scalar field, so you have the Newtonian force, and you have also that force that is associated to the scalar field. So there is an additional force for this one. Because of that, small galaxies should have an acceleration which is larger than large galaxies. So if you observe the galaxies, you should see that a very small galaxy should go much faster than a large galaxy, according to these theories. And if you take a theory like F of R, the difference between them is 4/3. The acceleration of this one is 4/3, or the acceleration of this one, sorry, is 4/3 the acceleration of this one. So actually it's not at all negligible. Any F of R gravity will have this property, actually. Any F of R gravity in the infrared. So this is just because the scalar field will be there or will not be there. Because one is very massive, the other one is not very massive. So that is one effect that we should observe. So far, it's difficult to observe these kind of things. To take particular galaxies, they should be more or less at the same distance, and one is small, the other one is large. It's a complicated thing, but theoretically, this is what we should observe. Another thing is that if you take now just a small galaxy, as we said, in the small galaxy, the scalar field is there because there is not much of matter. In the big one, you just suppress it. So imagine now you are looking to a star here. So you have some star in this galaxy, and you have a star in this galaxy. In this galaxy, the star actually, you take a star with exactly the same mass. If they have the same mass, etc., they should have the same luminosity that they produce and things like that. But because here you have the scalar field more, so when you take the star, so this is our star, for example, you have the Newtonian force, but at the same time you have this additional force, which is producing an additional effect. So actually these stars will be much more compact, and because of that, they will be much hotter than the other stars. So if you take objects with the same type of objects with the same mass, the stars which are in the unscreened galaxy should be much hotter than a star in in a screened galaxy. At the same time, their life should be much shorter, because if a star is very hot, it eliminates a lot of energy, and the life of the star will be much shorter. So here, in a small galaxies, you should have that the stars should disappear in some sense very fast because they use their fuel very, very fast because of the additional force that they feel, actually. So that will be another consequence of these theories.
That means you are imagining, no, that the scalar field should
Exactly,
be there.
exactly.
And then effect, if mass is less, then its effect would be dominating.
Exactly.
And in large galaxy, its effect would be negligible.
Yes.
Means you cannot see it.
Yes. So what we are trying to see is that if the scalar field exists, what will be the observables?
Consequences.
Yeah. So, and then we can check, we can imagine astronomers will be certainly smart enough to cook some way to observe that or not. So in the coming years, they might be able to observe that. So first of all, theoretically, we say, what are the differences between GIAN and these theories? And then we start preparing something to try to check it. These kind of things are not really checked yet. I will then talk about some experiments which have already been done. Another thing about these galaxies is that imagine that you take now this type of galaxy, so an unscreened galaxy. In the unscreened galaxy, you have stars and you have dust, just some dust also. Usually in a galaxy, you have mostly dust than stars, actually. Now you are inside the galaxy. If you have a star is pretty heavy, so it will suppress a bit the scalar field compared to the dust, which is very light, which will almost not suppress the scalar field. So just inside the galaxy, there will be a difference between dust and star. The dust should actually go much faster than a galaxy. So if you observe a galaxy, and we should be able to observe it, we should see that the stars, and here is dust, for example, the dust should go much faster than a star. Just because the star is much more heavy, so it will couple much more to the scalar field, suppress the scalar field, so there is very small effect. But dust, because it's very light, will be uncoupled to, will not make the scalar field heavy, so the scalar field will push a bit more and dust will have an additional acceleration. So we should measure some sort of violation of the equivalence principle. We have objects which do have acceleration which is different. One because it's very heavy, the other one with a small mass. You should violate the equivalence principle. That is another thing that you should be able to observe. Now if you go to compact objects, like for example a neutron star, a neutron star is of course emitting some gravitational waves, very little, but it's emitting gravitational waves. If there is a scalar field, it should emit an additional radiation. They call it very often scalar radiation. So it will emit much more energy. So we take two neutron stars, one where we consider that we have only GR, it will lose some energy, fine. And because it loses some energy, it will slow down, it will go a bit slower. And now, if you consider that you have a modification of gravity, it will lose much more energy, so it will slow down much faster. So studying actually these objects, like neutron stars, like pulsars, and how fast they rotate, you should be able to say if that is compatible with GR or if that is compatible with the modified gravity theory. Because in modified gravity theory, because of the presence of the scalar field, they will lose much more energy and they will actually start slowing down actually much faster.
How due to scalar field they will have much more faster, means they will lose energy? What is the reason?
The reason is that we talked about some, if you calculate okay, from a mathematical point of view first, if you calculate the gravitational waves and you want to know how much is emitted, so you take your theory of gravity and you expand the metric at second order, etc., and you get the energy of that which is emitted. Now, when you have a scalar field, there is a contribution from it. The thing is that the scalar field is not different than gravity in some sense. Let's take an example, a simple example, f of r. If you take f of r, this is just gravity. There is, at the beginning, no additional degree of freedom. So now we have seen that this is equivalent to R, the scalar field, that it's like GR plus a scalar field. It's equivalent, but it's just a mathematical thing. But fundamentally, what you say is that the theory of gravity is different. So gravitation waves, that energy which is emitted, depends on the theory of gravity. Because it is gravity actually at the end of the day. So if you have only GR, you emit some amount of energy. But if you modify gravity, the energy you emit will be different according to the theory of gravity, because it is gravitational energy. So if you change the theory of gravity, you emit more or less energy actually. So this is a direct consequence just of modifying gravity. And for the ones who already do this kind of calculations, if you have a G mu equal to T0 equal to 0 for GR, if you want to know the energy associated to gravitational waves, you have to expand this at the second order. So it's a bit much more involved. You have to expand at the second order in perturbations, because otherwise you cannot define energy. And once you expand that at the second order, you can identify something as the energy. Now, if you have a modification of gravity, something like that, for example, this will contribute also. So you expand everything at second order, and there will be an additional contribution to it, okay? But the energy has to be defined by expanding things at second order. Otherwise, you will not find any form of energy there. So let me go to some objects which give a bit more, maybe, constraints. Some are just nice. They don't put much constraints so far, but actually they are interesting because we are thinking out of the box in some sense. We are thinking of some new kind of experiments which are related to quantum mechanics. The idea is the following. You take ultra-cold neutrons. In the literature, they write it very often as UCN. So you just, with something, you just throw some neutrons like this. And the point is that if you take them very, very cold, they will have a velocity which is very small. And actually, you can reach something which is like 8 meters per second. So there will be very, very small neutrons. If they are very small neutrons and you throw them, what is happening is that they will behave like some sort of balls, and actually they will start feeling gravity. If they pass very fast, then they don't feel gravity. Gravity is in this direction, let's say. But if they are very, very slow, they will start feeling gravity. They will fall like that, and they will bounce, actually, and do something like this, actually, like a ball really bouncing. And here, usually, you put a mirror, and you get something like this. Now, actually, this system is a quantum system, so you solve the Schrödinger equation in presence of a potential. So when you solve the Schrödinger equation, this potential is just the gravitational potential, and we know how to solve it. It gives these airy functions, and the energy is discretized. Now, imagine that there is an additional force, that there is not only Newtonian force, but there is an additional force. You will have to include it here in the potential. And they have shown that in this case, the energies are shifted a bit. Very little, because it's a small modification of gravity if we do the test in the lab. So people are trying to see if with that, measuring the energies of these neutrons, you will be able to measure that shift actually. And because we have very good precision in quantum mechanics, we expect that maybe we will be able to measure something. For the moment, nothing has been observed, okay? But yeah, nothing so far. The precision is not that good, I have to say, for the moment, but so far nothing. Something much more problematic. This is just fancy, it's nice, but so far it doesn't give really good constraints. Another one which gives really good constraints and which killed a list of models actually is the vacuum chamber. The idea is the following, is that to take a vacuum chamber So actually, you really do vacuum here. The idea is to reproduce, in some sense, the universe. So, because in the universe it's almost vacuum, but you reproduce it in the lab. Okay. And what you are going to use is an interferometer, and with a laser, you send some signal like this. Then actually, you, as usual, you can split it into some two directions like this, for example. They come back, and then here you observe the interferences of these two systems. Okay, so you put an interferometer in a vacuum chamber. So what they imagine is that here there is vacuum. It's completely, there is no matter. So imagine that there is a scalar field, that the scalar field exists. Imagine that it is there. So we go always with this assumption. There is no matter here, so it doesn't couple to matter. So then that scalar field will start having some effects, actually. It should affect in some way this experiment. But what we do is that they added some cylinder here with some mass. So what's happening is the following. You have two beams, actually. One goes here, comes back and goes here, and this one is affected by the scalar field. The one here, the one which goes here, it goes through some massive object. So here, in this environment here, there is no scalar field. There is no scalar field because there is a mass which couples to the scalar field and screens the scalar field completely. So here there will be no scalar field, here there will be scalar field. So one beam actually will be affected by the scalar field, the other one will not be affected by the scalar field. Because of that, the interferences should change actually, should actually be shifted a bit, just because of the presence of that. So you remove that, you have some interferences, you put that, you should have interferences which will be shifted. And they have observed nothing. So that killed most of the theories of chameleon theories. If you want the reference, it's given in the document that you have, and they killed most of the chameleon theories, so which means most of the FOFA theories. The interesting thing is that this experiment, which is done so by some physicists, some experimentalists, has been done with one of the authors of chameleon. Chameleon is something which has been done by Curie and Weltman. These are the two people who cooked actually this theory, and Curie is the guy who was also involved in that. So he wanted, in some sense, maybe to see if his theory is working or not, but the conclusion is pretty clear at the end that that killed, in some sense, these theories. After that, he stopped working on that. Now he is thinking of some new theories, but chameleon theories might have been killed by this experiment because the precision was quite good here. It kills chameleon, it kills FOFA. Okay, so that is a quite interesting experiment. The other experiments, which are, some are just coming now, some they have been done since quite some time. Remember that I was telling you about this lunar laser range, which is measuring the distance to the moon. So you measure the distance to the moon, and if you have the sun, and you have the moon, and you have the Earth, what's happening is that if you have a scalar field which is present here, it couples to these objects, it couples a lot to the Earth, it couples just a little bit to the moon, and because of that, one of these two objects, the moon, should have an acceleration faster than the Earth. So because of that, they should actually, the distance between them should change. And so far, we haven't observed anything like that. So that is another constraint on these models. The last thing on this part is Edvosh experiments, which is called the Torsion Balance. It's this Cavendish experiment, which has been done since quite some time, to measure the Newtonian force and to see how much good it is, this law which goes like a potential, which goes like 1 over r, it's, the device is more or less like this. The device is more or less like this, is you consider some two masses here, M1 and M2, which are attached, and this can actually have has some torque, and you approach with some mass here, and this actually will move a bit because of the gravitational force between them. So the angle that it will produce, so if you have enough precision, the angle that it will produce, or how much they come close to each other, you can measure the force of gravity. So people are doing this. There is a main group in Washington. It's called the Edvosh group. And they test that since quite some time, and they didn't find any modification of gravity. But people were saying, yeah, but this experiment is made on Earth. So on Earth, there is a scalar field which is coupled to matter, so it's screened, so we don't observe it. So then they decided to do it in a spaceship, do the same experiment in a spaceship. It's called microscope. And the first result, so you take the same device, but you put it in a spaceship and you go far from the Earth in order not to have that scalar field coupled to the matter of the Earth. And they found the results were published this August, and so far they found nothing. So no deviation at all. This is the first result. They are going to publish something else next year with more precision. So in the upcoming years, actually in this 2018, 2019, they will give a really good precision about that. So keep looking to what microscope will say. That is pretty interesting.
So here means if scalar field is there, then the deviation angle would be more, no?
Yes. Yeah.
Some delta phi, little bit more.
Yes, yes. It will produce an additional force. If it will be more or not, have to think about it. But it will produce an additional. And because there is the Newtonian force, and there is the force produced by the scalar field.
So what exactly you are doing? You are just twisting this thing.
Yes, exactly. Okay. Most exactly is that when you twist that, you approach with some mass, so this one gets attracted. Oh, yeah. So then it goes a bit like this, but because actually this thing has a torque, it will go back. It will go back. But because it goes back, at some point of time there is in a way the force of gravity attracting it, so it will come back. But then it will do that. So it will start oscillating actually. So you can observe this oscillation. So people now they do it in a bit different way because this is the old way by Cavendish in the 19th century, I think. But this is how they measured the gravitation constant G actually. And but now they do it in a bit different way by taking cylinders. Actually, you have one cylinder, another cylinder, and if there will be a torque like this between the two cylinders, not using these masses, and they use a laser shooting on one of the cylinders, and it comes back. So when it's rotating, the laser actually is showing the position. So with the laser, you can have really good precision on how much it's rotating actually. So they reach really good precision about it. Yes?
All this setup is kept in a vacuum chamber, right?
Not this one. No, this one, yes.
No, I am talking about this one.
No, this one, no. Hold on a second. No, yes, sorry. Yeah, there are two things. One is that they put it in a vacuum chamber. The other one is, why the vacuum chamber is because also, I mean, if you don't isolate completely this, imagine there is a bit of wind, then it perturbs completely and it will start oscillating. And the other one is to eliminate electromagnetic force.
Right. But my question is, will the mass of the chamber also affect this system?
You have to put it large enough. So you put it large enough and you put at the center of it this device actually. So you put the border in some sense a bit large enough. But you can calculate it and see what will be the effect of it. But the main thing is not to put too small, because otherwise, yes, it's true, it makes some effect, to put it large enough and to put the device at the center. But the main concern about these people when they do that is the electromagnetic force. Because when you start putting them too close to each other, then there is electromagnetic force between electrons, etc., which is much stronger than gravity. If you want to test gravity at very, very small distances, then you have to suppress that. So this is why they use gold, actually, which is a bit better in some sense, more isolated for electromagnetic force.
Here in vacuum, in vacuum chamber, you are telling that this is a vacuum, but still you are putting the cylinder. So
Yes.
Except cylinder, the other things.
Exactly,
no?
exactly. So there are no particles all around it. So trying to reproduce in some sense the universe. That's what they try to do. Yes?
The scalar field is not screened by the splitter and the mirror.
It's not what?
It's not screened by the mirrors or the splitter.
Here, yes. In this region, it's screened. So in this region, because there is a mass, it's screened. In this region, no. Here, there is no mass. So at least the scalar field in this region should affect, but here it will be screened. That's the idea.
It is not screened by these mirrors which you use for reflecting.
No, there is always some effect locally here, but on all this part, it will not be. At the same time, they take a Fabry-Perot interferometer, so it makes it very often. It goes and bounces back, it's very often. So you will get a small effect, but you accumulate it during a long time, actually. So then the effect becomes larger. So, but you get always some screened part here, maybe here on the border, maybe when it passes next to this part. But then there is a region where it is unscreened, so then it will affect a bit and shift a bit the phase of that beam. So
here you will have interference pattern would be different, no, in both the regions.
Exactly,
Yeah.
exactly. Okay, so what to do actually with all that? One thing first, I mean, depending if you are interested by cosmology or if you are interested by gravity, I will separate both of them. One of them is, first I will separate it into UV modified gravity and infrared modified gravity. If you do UV modified gravity, so if you modify gravity at high energies, then you are completely free. There is no constraints at all. So for example, in cosmology, you can study inflation. Inflation, we need a scalar field. That is fundamental. The scalar field which we don't need is now. But at high energies in the very early universe, a scalar field is fundamental to explain the acceleration of the universe, and it's compatible with all observations. So if you are interested by adding some scalar field, and you are interested by cosmology, look at it in the very early universe in the inflation. And one part of inflation which has not been a lot studied is what comes just after inflation, which is called the reheating. The reheating is something which is not very well known, because what's happening is that imagine that we had a universe, and that universe is going to have an inflation, and it goes very, very fast. The problem is that expanding very fast makes that at the end of this expansion, the universe will be very cold, actually. It will lose a lot of energy just because you expand it a lot. So we will end, at the end of inflation, with a very cold universe. But this is not compatible with what we want. We want a hot universe, which is going to start producing particles and then cooling down, and that is the theory of the Big Bang. So because of that, you need to reheat the universe, and it's called the reheating. So that part is something which we don't know very well, and principally how it might affect the observations, etc. So if you are interested by cosmology and in the UV regime, I would say inflation and reheating are the best candidates in this. If you are interested, the other part also, but in this thing, if you are still interested by these theories, again, not to be to have a confusion. When I said that F of R gravity is dead, I'm talking about the models which were supposed to explain the acceleration of the universe today. But if you cook some F of R theory, which is explaining the acceleration of the universe in the early universe, for example, the Starobinsky model, this is perfectly fine. This is compatible with the observation. What is not compatible will be something like this. We have seen that there was two types of modifications. That is a modification which is important when the curvature scala is small. That is a modification which is important when the curvature scala is large. So that is a UV, this is an infrared modification. That is dead, that is not dead.
That is, last one is for dark energy, no?
Yes, exactly. So these are the models like that, which are changing general relativity at low energy. These are the models which are going to be difficult to make them compatible with the observations. But if you are interested of high energy, then you can go with F of R. It's perfectly compatible. You will have no problem at all, actually. Another thing continuing in terms of cosmology, which is developing a lot, is formation of structures. If you are interested by cosmology, I will really recommend to go in how the structures they form. Because so far, what we do about structures, what we know about structures, we use just Newtonian gravity. That is clearly not enough. If we want to go, we are getting more and more precision, and we have to start taking into account the theory of Einstein, means adding some relativistic corrections. So far, we just use Newton. I'm talking about the formation of structures, so when we are at small scales. And that is not enough, of course, because if you consider the full GR, it's too complicated. There are billions of billions of billions of stars, etc. You cannot make a simulation with all that. It's too complicated. In GR, the only simulation we know how to do is two objects, the binary system, two black holes, for example. But if you take billions of objects, you will never be able to deal with it. So because of that, people are doing simulations which are Newtonian simulations. So it will be good to add some relativistic corrections or to add a modification of gravity and to see what is happening, what are the signatures, if we are going to observe something or not. This we don't know, actually. So that will be interesting, actually, to study. On the black hole part, and on the black hole part, there are two directions interesting. One are studying the stability, either at the linear order, and most of the theories of gravity, and we are at high energies, so it's like a UV modification of gravity. That is motivated, there is no problem. You can study the stability of these theories, the stability of the black hole, actually. Most of the theories here, we don't know if the black holes are stable or not. So it's important to calculate these kind of things. The simulations, if you are good with simulations, you can go for full simulations. You take two black holes and you collapse them and it forms one black hole. We do it for GR, we don't do it for modified gravity. So we don't know at all what will be the real spectrum, the real form of the gravitational wave that we should observe if it was a modified gravity theory. Because the simulations are done only in GR. No one has ever did the full simulation with modified gravity. So that is a complete open problem. We have no idea about that. One thing that people started being a lot interested on is not adding a scalar field, but adding a complex scalar field. So you have actually a complex scalar field, and that gives not a real, like here, and that gives something quite interesting actually for black holes. If you want to read a bit about it, they are called boson stars, or they are called also non-topological solitons. In the literature, they are called either boson stars or non-topological solitons. What you can produce with that is a star, but very, very actually dense and compact, much more than a neutron star. So in some sense, it looks like a black hole. So people, there was some groups which published a couple of papers saying that the black holes that we have observed, maybe they are not black holes. Maybe they are these objects, actually. They are boson stars. That is yet an open problem. We are not sure yet. So it is interesting to study these objects to see what is the difference between a boson star and a black hole. So imagine a star, but extremely dense, which looks almost like a black hole. It's not yet a black hole, but it looks almost like a black hole. So it will have more or less the same properties. And so they are saying that maybe what we have observed, we say that they are black holes, maybe they are boson stars. So they are called sometimes black hole mimickers, actually. On the part of neutron stars, I would say that we have a big problem in modified gravity, which is the following. So this is something that you can also study. Imagine that you have a neutron star. So you have some matter. In general relativity, the problem is pretty simple. Outside, it's vacuum. You have Schwarzschild solution. Inside, you have some matter. You solve it numerically, and you get some solution. And then, of course, these two solutions for the moment are independent. You have to match them at the surface here. So there are some matching conditions. Okay, and then you have only one solution. The solution outside, inside, the solution outside, you match them, and then you have a full space-time, and that works perfectly fine. In modified gravity, you solve the solution inside, you get something. Outside is vacuum, as I said yesterday, most of the time is Schwarzschild, and we cannot match it. We have difficulties to match the conditions here. It becomes very difficult, actually. So people who are interested by compact objects, that is an interesting problem, actually, to try to match these two solutions inside and outside. If you cannot match them, then you will prove something amazing, that you will say that in modified gravity theories, neutron stars don't exist. Then you will rule out completely these theories, because of course neutron stars exist. We observe them. Because if you say that it's impossible to match this solution with this solution, means that this object cannot exist. So that is an open problem, actually, to try to check if really we can match the solutions or not. It's not.
You would like to match the solution on boundary, no?
Yes, exactly.
It should match, no?
Yes, they should, because otherwise they are just two independent solutions. It's just like we have a space-time here, we have a space-time here, but they are completely disconnected. They have to match in some way. So there are some called junction conditions that you have to actually consider here in order, which is more or less the metric and the derivative of the metric. Junction conditions, and you have to match them in order to have a full solution from 0 to infinity. And so at the surface of the star. Here we have matter, here there is vacuum, and you match it. In GR there is no problem at all, really no problem. In modified gravity it's complicated. Another thing about neutron stars, which is interesting, is that when you take a neutron star, here the matter inside, you have to take an equation of state. For the people working in the field, they know that very well. You cannot solve the equation just like that. You have to consider that some relation between pressure and density. For example, you can say that the pressure has this law compared to the density. And this will come from some different models in particle physics, because more or less here you have high density, so people are using nuclear physics, QCD mainly, mostly, to cook some equation of state. So you get some equation of state like that. The problem is we don't know what's happening inside the star, actually. So we don't know what is this equation of state. So it's a physics which is a bit unknown, in the sense that the only light that we receive comes from outside. We don't have information of what is inside. Gravitational waves will give us information of inside, but so far we don't have enough precision, so we don't know what is the real equation of state. Is it here 4/3? Is it 2? Is it 5/3? Is it? We don't know. So every time you take an equation of state, you get a new solution, and then you get a new physics, etc. So some people tried actually to develop some quantities which are independent of this equation of state. So you can take any equation of state, the parameters that they cooked are completely independent of that, and that is very interesting, because then you can see if the theory of gravity works or not. It's called I love Q. So you can check in the literature about it. There are two parameters, I and Q, and the parameter love. And in general relativity, these parameters, I, love, and Q, are related in some way. There are some relation between these parameters. In modified gravity, you might get another actually relation between them. Why I'm saying that is the following: is that imagine that you observe something strange for neutron stars. Then you can say, oh yes, I just discovered that with this neutron star, GR doesn't work. That we have a modification of gravity because it's not compatible with the model that we had. But someone can say, no, actually, you just change the equation of state. I have so much freedom here, I can always choose some equation of state to make things compatible with the observations. But here you just remove one of the parameters, which is this equation of state. You say, okay, whatever I do, these parameters are independent of the physics inside. So in that sense, it depends just on the theory of gravity. So if you have GR, or if you have a modified gravity theory, you will have a different relation between them. This is calculated for some theories of gravity, but not for other theories of gravity. Okay, so let me finish a few comments about that for the people who are just starting in the field. The first thing to say is that I would say that the most important thing is to learn tools. Because imagine that you become specialized in one model, that you learn F of R gravity. You become an international expert in F of R gravity. And then tomorrow there are some people cooking an experiment like that and they say it's dead. And next day you are jobless. You have nothing to do. So you lost 20 years working on some model and they tell you it's wrong. So the most important thing is to learn tools about how to study some models. The tools are either analytical tools like theory of perturbations, linear perturbations, nonlinear perturbations, how to deal with data analysis, or full numerical things. There are many codes in cosmology and in gravity. In cosmology, you have all the things related to CMB, CMB fast, you have n-body simulations, you have many codes actually which exist, or how to deal with perturbations, how to study all this, etc. If you know these tools, and tomorrow they tell you this model is wrong, you can go to another model and use the same tools because you have that background which is strong. So more than learning about some models, learn the tools actually. The mathematical tools or the statistical analysis, etc. I would say that this is the most important thing. Another thing is motivation. I would say that we have, of course, always to motivate the models. It's not just because it's popular and we should work on it. And one of the best motivation is to consider quantum corrections to GR. So because this is the thing that we don't know much. So if you can learn quantum field theory in curved space-time, the book by Davis and Birel, that will be fantastic because then you can add some corrections and then study this model and study what is the phenomenology because you have already the tools, etc. So that is a very interesting thing. Now, the last comment about some aspects which I found interesting for me is to work in dimensions which are not 4, for two reasons. One is 5 dimension, one is 3 dimensions. Why I found it interesting, it's not the real world, but we can learn different things. We can say that it's stupid because in both cases we just miss the reality, which is 4 between them. But what do we learn from that? One is here what is called duality. In the sense that, imagine that our world is 4-dimensional. We have a 4D theory of gravity. Okay. This is the real world. It's 4-dimensional. But actually, the theory of gravity we know is Einstein theory of gravity, and that is not enough. We want a quantum theory of gravity. Plus quantum corrections. The thing is that the duality tells us that maybe this is equal to a 5-dimensional theory, classical theory of gravity. So there is a duality, there is a relation between them. You work in 5 dimensions, okay? You work with a classical theory of gravity. There is no quantum at all. It's completely classical. But what you will find there is in some sense equivalent to 4-dimensional quantum gravity. Because we don't know how to do quantum gravity, you work in 5 dimensions, you have classical gravity, and that will give us some information about that. So in that sense, it's very interesting. Let me give you an example. A long time ago, in the 70s, I think, some people calculated what is the quantum correction to the Schwarzschild solution. So you take a black hole, which is Schwarzschild. So we know what is the metric. This is completely classical. And you start calculating what is the loop correction, the quantum correction to it. And they found something that what is in the metric is that you have this, which is the Schwarzschild solution, and you get some correction which goes like R3. This is a quantum thing. A quantum correction to the Schwarzschild solution. And the thing is that in 2001, people started working with brain models. So started working in 5 dimensions. And if you work in brain models, you will find actually that you get something which has exactly the same structure. But this correction here comes just because of the extra dimension. It's just a correction which comes because of the extra dimension. So you see that you have, in some sense, the same picture here and here. You get the same correction. You don't get 1 over r squared, like a charged black hole. You get 1 over r cubed, actually. This is the quantum correction to Schwarzschild solution, and you get the same thing. Now we have to develop more examples. I'll tell you just one result that I'm working on. For example, you remember the Starobinsky model? I was saying that it is quantum origin, actually. That, again, in the 70s, this was not in the 70s, it was even 60s. But in the 70s, some people actually calculated the correction to, in this case, it wasn't in black hole, but in cosmology. And they found that you get some correction to GR, which goes like that. You get 2 corrections. So you get a theory like this. You get GR plus 2 corrections, which are quantum corrections. So here it's in the context of cosmology. We are not talking about black holes. And they found this. The point is, this term here, you can get it from an action, which is the action of general relativity. This term here, you can get it from an action,
quantum correction?
Actually, it's one quantum, but you can separate it in two parts. I'm just separating in two parts because one I can get it from an action, the other one I cannot. But it's one loop correction. It's they are at the same order, actually. There is not one which is an order larger than the other. So this was done in the 70s by these people who published this book, Quantum Field Theory in Curved Spacetime, with Davis, Birrell, etc. And there were some other authors. So they found this. The point is that this you can get it from this action. This you can get it from this action. And then Starobinsky later on said, okay, let us take this only. And we call it now the Starobinsky model. And you remember that it's compatible with inflation, etc. So we are very happy with it. The problem is that this term here, you cannot get it from an action. You get a term, but you cannot get it from an action principle. So you cannot find some action. When you do the variation, you get this term, which is a bit strange. So you get some quantum correction, but you cannot get it from a classical action. The point is that this is something that we are working with a student that we will publish soon. You can get it from a brain model if you go in 5 dimensions, actually. So it's exactly the same picture than here. If you work in 5 dimensions, then you reduce your theory in 4 dimensions, you get this term. This one, actually, it's this. Is this, but in 5 dimensions. So actually, again, you see this duality, this relation between a classical theory in 5 dimensions and a quantum theory in 4 dimensions. So if you want to learn about quantum gravity, maybe you should go to 5 dimensions. So that is one motivation to work in 5 dimensions. There is another duality which I'm not working on, but I have colleagues working on that, and maybe I will also start working on it, which is called ADS-CFT, which is also done in 5 dimensions, but I will not mention it, which is another area also very interesting, etc., which is another type of duality.
To get the second quantum correction, you have to go to 5 dimensions.
Exactly.
But is it really needed to take the second correction also?
Yes, because why the calculations, they give this. This is what your calculation is giving. So you cannot say just, no, I will disregard this term. It comes from the calculations. So we cannot say, no, it's 0, actually. It is there. And this coefficient is not a free coefficient. It's like pi divided by 3,612, something like that. So it has a number, actually. We cannot fix it as we want, actually. So the thing is that, so when it was published, in their paper they said, yeah, we don't know what to do with this. We cannot get it from an action. People worked on it for quite some time. And then later on, Starobinsky said, okay, because we cannot, let us just look to the phenomenology of that. So when I was saying that alpha r squared is a quantum correction, it's half true, but because it's not the full picture, you need another term to have the full quantum correction, actually. It's not the full picture of it. And because we have a very short time, let me go fast on 3 dimensions. Why it is interesting to work in 3 dimensions. The reason is, imagine that you work in 3 dimensions, and so your matrix now is a matrix which is 3 by 3. So you have not 10 components, but only 6. 6 degrees of freedom, or 6 components, I would say. Okay, these are not yet the degrees of freedom. Remember that you have some constraints. First of all, you can always change your coordinate system, remember. Changing the coordinate system, you can always suppress some of them. Here, how many coordinates you have? There are 3 coordinates because we are in 3 dimensions. So this will bring 3 constraints. At the same time, we have what is called the Bianchi identity, which brings also 3 constraints. So you have 6 constraints, you have 6 components, you have 0 degrees of freedom. In 4 dimensions, you have 2 degrees of freedom, which are the gravitation waves. the cross mode and the plus mode. These are the modes which are propagating. In 3 dimensions, there are no degrees of freedom. If you walk in 3 dimensions, there are no gravitational waves, there is nothing there. So then, if there is no gravity, you don't have to bother about quantizing gravity, because there is no gravity. So then it makes life much simpler, actually. So what you can think of then is the following, is that you can say, because I don't have to quantize gravity, because there is no gravity, there are no gravitational waves, there is no graviton. So you take a theory in 3 dimensions, like this, G mu equal to T mu, for example, like Einstein, or any modification of gravity, and you quantize only the matter. You quantize just the matter actually. You don't need to quantize the full the geometry, because there is no graviton here. There are no gravitational waves to quantize. So you quantize just this, and then you have a quantum theory of gravity. You have a theory which is quantum. Then you can see what are the effects on black holes, the effects on cosmology, etc. And this might actually, it's just a belief, that it might give us some information on what's happening in 4 dimensions. So as I was saying, there was this interesting paper published recently, is that if you work in 3 dimensions and you have a naked singularity, so we don't have horizon, so you start with a naked singularity, then you add some matter and you quantize that matter, it produces actually a horizon. So just from a quantum effect, you cannot have a naked singularity. Even if you have a naked singularity initially, quantum corrections are going to produce a horizon and hide the singularity. So this might happen also in 4 dimensions, but it will be more complicated. It will take time for people to show it in 4D, because we need to quantize gravity. But in 3 dimensions, you do it easily. So in 3 dimensions, you can walk there, you can try to study cosmology in 3 dimensions, add some quantum corrections, and this will give us maybe some informations about 4-dimensional. Okay, I finish with that, more or less. I have 10 minutes if you have some questions, final questions, yes.
Suppose instead of going some higher dimension, suppose I choose 2 dimension, and as per topological view, we construct some structure and explain all the observations and explain all the observed observations on that structure. Then is it right that we are again working? We are again. Is it right? I mean, the theory is modified. Because as per Lovelock theorem, you have said that if we go some higher dimension or reduced dimension, then the theory will be under modified. And
I'm not sure to get the question. When you go to higher dimensions, okay, let me say something. I'm not sure if I'm answering the question. If not, just please ask again. If you walk in higher dimensions, you have more degrees of freedom. From a 4-dimensional point of view, it looks like a modification of gravity, always. You will not get only GR. So the point is, this is why you can think of these corrections which appear, like, for example, what I was talking about, these Galilean theories, like maybe just a quantum correction. Because you work that in 5 dimensions, they appear when you reduce it to 4 dimension, so you can think of it in this way. Not always. I mean, you have to be careful. It's not that you just take a theory in 5D, you reduce it to 4D, and these are quantum corrections. But in general, you will get this picture, actually. It's not trivial. It's not sure at 100%. But what I'm trying to say is that working in 5 dimension, it might give us some information of 4D quantum gravity. There is no theorem about that. It's just a conjecture.
Suppose I make a torus from 2 dimensions and successfully explain the observations
yeah.
on that structure.
But here you are talking about topology.
Topological view, right?
Yeah, the thing is that all the theories that we are defining, the theory of general relativity, they are local theories.
Right. But
They don't care about the full topology.
instead of diffeomorphic transformation, we go homeomorphic transformation because there is a continuous patch.
Mm-hmm.
Uh,
You don't want to be differentiable? You don't want to be differentiable?
yeah.
Why?
Because we have two different patches for coordinate transformation from
Yes.
one patch to other.
Yes.
Diffeomorphics. But instead of going to these two, instead of choosing these two patches, can we choose one single patch and form a such a geometrical structure from that patch and subsequently?
I'm not sure to get the question. The diffeomorphism is just an invariance about the change of coordinates. It's not that we are selecting some subspace or some patch or something like that. If you want to violate that, consider something which doesn't have diffeomorphism. This is also done. People are working on that. I don't think it's necessarily interesting, but people are violating that symmetry, saying, yeah, maybe why not? And one of them is massive gravity. Massive gravity, you break that symmetry, in some sense. But I'm not sure it's an interesting road to take.
Yeah, you are taking in 3D and you are telling that there is no gravitation.
Waves.
And if there is no gravity, then how we can say we are quantizing quantum gravity thing?
No, yeah, this sentence is just between quotes, actually. No, what we are, yeah, the D was there, quantized matter. No, what I'm saying is that, yes, the thing is that in 4 dimensions, I should not call it quantum gravity. I should call it quantum world or something like that. It's just that we are looking to a quantum correction, how it will affect a black hole, let's say. That's the idea. Imagine you have a classical black hole and you want to see quantum corrections, what they will, how they are going to modify that structure. Is the black hole going to maintain the same shape? Is it going to be modified? Is the singularity going to disappear? Something like that. So then you just look to implication of quantized matter on the geometry. In 4 dimension, it's complicated because you will have to quantize matter and geometry. And this is the difficult part. You can always quantize matter. Geometry is difficult. There are different roads, but it's tough.
In fact, we have done that part with conformal quantization and studied the behavior of conformal quantization near the space-time singularity, near the black hole singularity mass.
Yeah.
And then it doesn't remain stable. And
no, there are different roads. There is low quantum gravity, there is non-commutative geometry, there is string theory, etc. Which road we take, there is no clear picture, because each of them has some internal problems also, but also we cannot test them so far. So some of them, they try to put some very broad kind of assumptions to make them predictable. For example, some people, they have kind of put some constraints saying that in loop quantum gravity, the photons which are emitted from an object, for example, or any energetical particles, they will have a different speed if they have different energies. The ones which have a very large energy should have a speed much larger than the others. They don't all go at the speed of light. So the speed of light depends on the energy, actually. And that has been disproved. But it doesn't mean that loop quantum gravity doesn't work. It means that this specific model, but the others, we cannot check them. So then it's matter of taste. So is it string theory, if we want to live in 10 dimensions? Is it loop quantum gravity? Is it non-commutative geometry? It's not clear, and also they don't solve the fundamental problem I was talking about, the cosmological constant problem. A quantum theory of gravity should solve it. If it doesn't solve it, it means that the picture is not complete.
There is a problem. You need to write your clear address on that. because Vice Chancellor is out of station. He will be back only on Tuesday, so he couldn't sign this certificate. As per MHRD, it has to be signed by Vice Chancellor. So I'll get it signed on Tuesday, and we will post along with grade sheet. So please clearly write your address. Clear. It should be very clear address, right? And you will get. And we are on the WhatsApp group. You don't worry. It will be done. I apologize for that because it is not my hand. We have signed. The local coordinator has signed, but VC is not available. We were waiting, but he will come only on the Tuesday. He is in Trichy, in their institute, NIT Trichy. He is visiting NIT Trichy, so he will be back only on Tuesday morning. So Tuesday morning I'll give it, and we'll get it signed on Tuesday, and then we will send by post. Because anyway, grade sheet has to be posted, so this will be also posted. But if you need anything in writing for your claim and all, I can do in the letter file. I can write that you have attended and the certificate will be posted later. That I can give you in writing, if anybody wants that, right? But it is, last time we posted notes also, so don't worry, it will be done 100%, right? Because it has to be signed by Vice Chancellor as per the MHRD. Nobody else can sign. And he is on leave from Thursday. All right. Now you can ask us.
Sir,
Yes.
I have one question.
So please write your address.
You have
Clear
calculated
address.
scale parameter for CMB, and it
Scale,
is equivalent to 1 upon 1200. How
yeah.
did you get it?
Which thing? Which part?
This one.
No, this is, it's not calculated. It's to say that, okay, the universe is expanding, and there is, at the beginning, you have particles, the photons which are interacting with all particles, etc., so they are coupled to matter. And there is a moment which is called the decoupling, when the photons are completely free and they can move actually without any problem. So this you get it from the CMB, it's an observation, and it's for a redshift around 1100, something like that. It's 1100 or 1200. So from that you get the scale factor, which is 1 over 1 plus z. So it will be this 1 over 200. So it comes from actually an observation. The moment of the decoupling, the moment where the photons actually, it's most exactly it's that first you have the photons which are interacting with the particles, but you reach a moment where the temperature is low enough and actually the electrons are captured by the protons and they form some neutral atoms. So now actually the photons, they don't interact anymore with these structures and they just go without any interaction. So in that sense they decouple. So these photons are completely free. So you can do the calculation and find that this is actually the moment of decoupling.
So when you were proposing a dark matter, you were proposing it's outside the galaxies or it is also inside?
It is inside and outside, but it's mostly the structure will be something like that. So you have a galaxy, and the galaxy is like a gravitational potential. Okay, and these particles, this is the halo model for dark matter. What it tells us is that, okay, this dark matter is everywhere, but it will form some structure around. What is happening is that because there is a gravitational potential here, they fall into the galaxy, okay, But the point is that because they don't interact with matter, they will just pass. If they were interacting by electromagnetic force, for example, they might be attached and form structures, etc. But because they don't interact with the others except gravitationally, and they feel gravity, so they fall, so they will just continue up to here, for example. When they reach this point, they get attracted again. So then they come back. So then they spend their time actually moving around like this, actually. Okay? So most of the time you would find them in some sense around like this, and they just go around. If they were interacting in a different way than just gravity, then they will start forming structures. They will form actually, because if you take two particles, they hit each other, you will have just an elastic interaction. They hit and they go away. Imagine now that you have electromagnetic force. When they hit each other, if there is enough electromagnetic force, they can bind, and you can form two objects, two particles, like a proton with an electron or something like that. So you start actually getting some structure, and you start accumulating that, and you form a planet, you form a star, etc. If you don't have a planet which is a dark matter planet or a dark matter star, it's because they don't interact except by gravitational force. So they feel the gravitational potential of the galaxy, they fall into it, but they don't interact, they go away, and once they are far away, they are attracted again, they come back, etc. So they are just going around, actually.
And sir, does the scalar field proposed by the modified gravity,
Yeah.
that also explains?
No, the modified gravity, modified gravity or monde? No, this is usually people are using this theory which is called monde, and I said to be careful because people they also call it modified gravity, but for me this is another type of modified gravity. So in this case they don't add a scalar field actually. It's just a change of the Newtonian force. You just say that. Huh? Yes. Yes. So this is it's a modification of Newton force actually, and this is what it means: a modified Newton dynamics, something like that. But if I'm talking about modified gravity, I was talking about this other type of theories to explain the acceleration of the universe, etc., not necessarily dark matter. So for dark matter, just to finish this point, these particles here, which do not interact by the electromagnetic force, but mostly by gravitational force, maybe the weak force, there are some candidates in particle physics which are coming mostly from supersymmetry and things like that. So people are trying to look at them, but it's difficult to find them because they interact very little actually.
So now we have detected the gravitational waves. So like dark matter only interact with the gravitational waves.
Mm-hmm.
So from this way, can we, with the help of the gravitational wave detection, can we infer the type of that dark energy or dark matter? Because
no.
If it's interacting, so there will be any significance.
No, the thing is that we don't observe directly gravitational waves. We observe the effect of it on matter. What we observe is really matter. For example, the standard thing that you study in class when you do GR, you say that I'm taking a circle of particles like that, and there is a gravitation which passes, and this will start oscillating either in a cross or plus mode. So then you observe the effect on matter actually. If you take LIGO, it's the effect on an interferometer, so which is matter. So this is what you observe. You don't observe directly the gravitational wave. So now, if you don't observe dark matter, you will not see the effect on dark matter, because you don't observe dark matter. If we could observe dark matter, we would be able to say something about gravitational waves. But because we don't observe dark matter, we will not know what is the effect on it, because we don't observe directly the gravitational wave.
Can we consider black holes as dark matter?
There are models for that, but it seems not to be enough in the sense that to consider that there are some black holes which have been formed in the standard formation of black holes is to take a star which is collapsing and form a black hole. Some other theories are saying in the very, very, very early universe, you had fluctuations, quantum fluctuations, and this quantum fluctuation could actually collapse and form a black hole. These are the primordial black holes. So maybe you could have some of these black holes somewhere. Another way is also produced by some theories of extra dimensions, which are producing some mini black holes. Small black holes like the size of a particle, and you could have a lot of them. But if you go with these primordial black holes and this, how many of them you should have, it's not compatible. Part of the dark matter could be that. Part of the dark matter could be neutrinos. Part of the dark matter, but to explain all dark matter with this, it's not enough actually. So it can be part of it, yes, that's for sure.
How many other components can be considered as dark matter?
Most of the time people are considering these particles from supersymmetry, like the gravitino, for example, which is the super partner of the graviton. This is one candidate. I have a friend who did his PhD on that. Then you have plenty of, actually, I don't remember the names of it. It ends always with ino when it is from supersymmetry. You have all this leptino or something like that. So then you have actually a zoo of particles. But they have to be at low energy enough. We need cold dark matter. We need cold dark matter because if you have hot dark matter, means that if you have cold dark matter means that the dark matter has a small velocity. Hot dark matter, they will actually go too fast. And if they go too fast, every time they hit a particle in the galaxy, they will push it away. And then the galaxy will have difficulties to form. That they go too fast, they hit everything, and galaxies will have really difficulties to form. So we need slow, actually, particles. If they hit, they move a bit the particle, but not too much, so the galaxy can form. If you have too hot dark matter, then you will not form the structures that as we see. So you need cold dark matter. This is how actually we cook this thing of lambda CDM, lambda and cold dark matter. It's cold because you want structures to form actually.
Has its role in the formation of galaxy?
As?
Role
Yeah.
of dark matter.
Yes.
In the formation of galaxy.
Yes. How strong it is? How? What? Sorry.
Does it have role, any role, you say?
Any role in forming galaxies?
Yeah, no, fundamental actually. It's not only to explain, dark matter is not only to explain that velocity, that the stars which are far away from the center, that they have large velocity star. It's also for forming the galaxies. What is happening is the following, is that imagine that we are in the very early universe, and you have some part where you have a bit more matter, okay? But the point is that, and so you have some matter coming here, and you form a structure which is a bit bigger, etc. But at the same time, there is radiation actually. So you have photons there. And we are in this very early universe. It's like a soup of particles, etc. And this radiation is interacting a lot with matter and producing a pressure towards actually the outside. So then, actually, all these particles are scattered away. You should not actually form structure. All the particles are going to go away. So then you will have difficulties to form structures. But dark matter, the very interesting thing, because here you will have matter and dark matter. Dark matter does not interact with radiation. So all matter will go away. So this is all the matter because of that pressure from radiation. But dark matter stays here because it doesn't interact with radiation. After decoupling, when radiation is not interacting anymore with matter, now you have dark matter here at the center, and all that baryonic matter will fall back. Because you have now something, it will fall back and you start forming again the galaxy. If there was no dark matter here at the center, you would not form galaxy actually. So they are fundamental for the formation of the structure.
I think because we have exam now, 11:30.
Okay.
So already
Yeah, sure.
11:50. You have quickly tea and then come back for exam.